All right. Thanks for coming on the day before fall break. 4 things coming up. You don't have a mastering due till next Wednesday, but it's next Wednesday and next Friday, and it's covering this. We're going to finish chapter 5 today, so the mastering next week, you'll have seen everything for it by the end of today. So if you have time over fall break to start working on it in May, you can get ahead a little bit. We'll do a group quiz today, and it's going to cover chapter 10, so it's going to be like the Vesper stuff, like you did in lab this week. So you should be super smart about Vesper and structures and those stuff structures. In case your lab instructor forgot to remind you, there is no lab for anyone next week. No lab regardless of day. And I'm going to make a small change to our syllabus. We're going to do chapter 5. We're going to finish that today, and then when I see you next Wednesday, we're going to go to chapter 3. The syllabus says chapter 6. We're going to go to 3 instead. So, I know, super important change to the syllabus. So. All right, was everyone able to watch the videos and catch up on, I'll pretend those are all yeses, excellent. So, the video covered the first half of chapter 5. So everything about the ideal gas law. And so the second half of chapter 5 is using the ideal gas law to make predictions about gas behavior. Like, how do we know why does gas behave the way it does, and it's based on the ideal. Yes, I skipped one slide.
Oh, okay.
Yeah. Yeah, no, there's this one about stoichiometry.
Yeah.
We're going to skip that and do that later.
Okay.
Yep. Mostly because we haven't done stoichiometry yet with things other than gases, which is why we're going to go chapter 5, then chapter 3. And then we'll come back to it. So when we are talking about gases, there's a few terms we need to use in order to describe what's happening, especially when we have a mixture of gases, more than one gas in a container. The first thing we talk about is the partial pressure, which is the pressure of an individual component in the mixture. So if I have a mixture of gases, 5 gas A and gas B in my container, each contribute a pressure to the overall pressure. And so in math terms, I could say that the pressure of A and the pressure of B is equal to the total pressure. Right, so I have 2 gases in my thing, and each of which have some amount of pressure. And so altogether, it must make the total pressure of the system. Which is Dalton's law. So Dalton's law says the total pressure of the mixture, which is this guy. Whoa, super catchy. Anyone else sneezes or coughs? Okay. The total pressure, right, this guy right here, of a mixture of gases is just the sum of each pressure. So it's the sum of A and B. All right, so that describes Dalton's law, that pressure of one plus pressure of the other equals the pressure of the total. All right, so in order to be able to calculate these individual pressures, we have to use a new quantity called a mole fraction. A mole fraction is a dimensionless quantity that expresses the ratio, right, which is a fraction, those are the same things, of the number of moles in one component to the number of moles in all the components, which would be total moles. Right, so if I'm talking about the fraction of ladies in here, right, I would count all the ladies and divided by the total number of people. Same thing. So a mole fraction takes the quantity of moles of gas A compared to the total number of moles in the entire container. So it's just a fraction of how much of the whole. Has everyone got that so far? And here is a picture in case my words have been confusing. Here's container number 1 with gas 1. Here's a picture with container 2 with gas 2, and I put it together. They add up to all the same ones. All right, so here I have 1, 2, 3, 4, 5, 6. 6 gases. Over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, if I add them all together, I now get 16. So math and pictures and words, you guys should be totally on it by now. Yeah? All right. So you guys look ready for some algebraic rearrangements? Yeah, yeah. And we're going to use our calculators later. Whoa, I know, it's craziness in here. It's a crazy Friday. All right, let's see if I can zoom in one. There we go. All right, so knowing that the pressure total is the pressure 1 plus pressure 2, right? That's Dalton's law. And the ideal gas law. So I have Dalton's law. All right, so I have the ideal gas law and Dalton's law. What letter do they seem to have in common? P, which means I can now do some substitutions in for each one of them. All right, so first, let me work on Dalton's law first. So I now have pressure of gas 1 and pressure of gas 2. I have this relationship that relates pressure to volume, moles, gas constant, and temperature. So I can rearrange these two to really say all right, all I've done is rearrange it and put some subscripts there saying that pressure 1 is related to the moles of 1, RT over V. The pressure of 2 is related to the moles of 2, RT over V. Which means I now can combine those and say that the pressure total good, right? So all I've done is I've pulled out those ends, and now I've just plugged them in for what I had before. All right, now I want to get all the ends together and all the RTVs on the other side. Well, on the other side of the plus sign. So far, not too magical so far. All right, if I only have 2 components in there, how many moles am I showing in my math right here? Is it the total moles or is it some of the moles? It's the total moles, right? So I could actually say look, I'm right back to where I was. Back to the ideal gas law. So the pressure of the total is equal to the moles of the total, RT over V. So I just did a circle. I did a math circle. I started with that. I ended back where I was. Nobody seems very impressed by that. Super impressive.
Oh, wait, no.
No squared. It's just I factored. Put all the ends together and.
I was looking to the end.
Oh, yeah, no, sorry. I should have spaced them out better. All right. since that wasn't super impressive, let's do another algebraic rearrangement, and maybe you'll be more impressed this time. Seems unlikely. Okay, so this gives us all right, so that's total pressure with total moles, which is great. But it's actually more interesting to figure out how many moles are contributing just to the pressure of 1 and how many moles are contributing just to the pressure of number 2. So going back to this up here, this P1 equals N1 RT over V. And looking at this total moles, what do you notice about these two particular equations they have in common? Like, what exactly is in common with them? RT and V, right? They're all constants, which means I can do some mathematical rearrangement. What can I now do to simplify this? Cancel a whole bunch of stuff out, right? And now I have moles of 1 divided by moles of the total. What did we just say that was called? Mole fraction. There it is. And mole fraction is so cool, it gets big letter X. I guess they ran out of letters. They're like, give it an X. That's what we got left. And so this is specifically, in this case, P1 over PT equals N1 over NT. That's the mole fraction of gas number 1, right? It's the fraction that's just the first part of the gases. All right, if you have a calculator handy, go ahead and pull that out because we are going to take our new equation for a test drive and see how awesome it is. It's pretty exciting. All right, let me clean this up so everybody can see it. Okay, so it's the same equation, I just rearranged it. So either you're looking for the mole fraction or you're looking for the partial pressure of somebody. So same equation, but if I boxed it, it probably means it's super important. Hint, hint. All right, so let's say I have a sample of natural gas that I know contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of butane. I know the total pressure, but I want to figure out what is the partial pressure of only the propane. So we're going to use this one because I'm looking for a partial pressure. Okay, do we know PT for this particular system? Do we know the total pressure? Yes, it's given to us. Do we know the mole fraction yet? No, so we're going to solve for the mole fraction first and then plug it in. All right, so I want the mole fraction of that one. So that's going to be the number of moles of just this over the total number of moles. All right, so which numerical value should I put on the top of my fraction? Yep, 116. Then how do I go about figuring out the total number of moles? Add them all together. Good. All right, so tricky math so far, right? All right, so 8.24 plus 0.421 plus 0.116. Make that an 8 with sig figs. All right, 0.116 divided by 8.78.
That's supposed to be 8.7.
8, that's an 8. Yep. Sig figs. So it's going to be 7, 7, but I can only have 3 sig figs. So. All right, so now what do I do with this new x? Where do I put it? Right there. Good. What units should I have on P? Atmospheres. So out of the total pressure, the 1.37, the pressure of the C3H8 is contributing 0.018 atmospheres total to it. Looking at the 3 components, the 8 moles, the 0.4 moles, and the 0.116 moles, is the C3H8 the greatest contributor or the least contributor in terms of moles? Right, least contributing number of moles, which makes sense why it gives very low pressure compared to. All right, you want to do another one or move on? Do another one? Okay. Let's see if I can come up with something clever. All right, so let's say we have a sample of gas that has 4.97 moles of ammonia, 8.47 moles of methane, and 10.82 moles of oxygen. I know the overall pressure. I would like to find the partial pressure of just the CH4. So what's the first thing we have to do in order to solve it? Yep, we need to find X. So what value of the 4 values in my question do I put on the top of my fraction? 4, 8, 10, 5? The top of the fraction? This guy, right? So then how do I go about figuring out the bottom of the fraction? Add them all together. Does my X have units? Right, because it's moles over moles, so they cancel out, so it's no units. All right, so then, what number do I plug in for pressure total? And then what units would that have? 8 units. Those aren't so bad, right? Which makes sense. If you look at the total moles, was that 18, well, a little more than maybe 19 and 5, 24. 24 moles altogether. The 8 is about a third of the moles, which gives it about a third of the pressure. So, that makes sense. All right, good. Let's talk about the tricky part of gases. I will talk slow if you don't have the PowerPoints, or you may just want to make a note to read the PowerPoints later. It's a lot of notes. All right, so a gas is composed of molecules that are separated from each other by distances far greater than their own dimension, right? So if I have a gas molecule here, the next one is greater than 1 angstrom away, right? They're pretty far apart. And these molecules can be considered just points in my gas, that they have mass, but they're very, very tiny, so they don't have very much volume. We assume they're always in constant motion, and they're moving in random directions, and because of that, they're often running into each other, right? If one gas is zipping this way, it's going to run into one coming this way, and that's fine. They're going to bump into each other and fling into opposite directions. So this is a picture of an elastic collision. So it's like when you're playing pool, right? Your cue ball hits the other balls and they bounce off in opposite directions. If you played that with Play-Doh, right, and you use your cue ball and you ran into a ball of Play-Doh, they would stick together, that'd be an inelastic collision. So gases don't do that. Gases have elastic collisions like pool balls. Gas molecules don't attract each other, nor do they repulse each other. They just would prefer not to be near each other. Which then means we can say that the average kinetic energy is proportional to the temperature. Right, so as the temperature of your gas gets hotter, they have more kinetic energy, they zip around more. If you cool it off, they lose their kinetic energy and they don't move around as much. And if I have two gases at the same temperature, we assume them to have the same kinetic energy because they don't have very much volume and their collisions are completely elastic. So, using what we know about gas laws and this new kinetic molecular theory, we can see how this is going to play out in everyday life. If you don't have this slide in front of you, I'm sorry. I'll leave it over here. So, Ke, right, is kinetic energy. This little m is mass, and this kind of U-looking thing is velocity. So the kinetic energy is directly related to the mass, right? They're both in the same equation. So kinetic energy has a direct relationship to mass. And so another way to write this, to talk about, instead just, this should be molecular mass. We want to talk about it in terms of moles, right? Because all of our gas laws have moles involved in them. And so we're going to rewrite this equation to involve moles. I can derive this for you, but I'm guessing no one really cares. If you do really care, come by my office. We can walk through from here to here. But in 10 years, no one's ever taken me up on that offer. So maybe you guys will be the class that's like, yeah, I want to derive some equations. Probably not. All right, this guy is Avogadro's number. This is just regular mass. And now this U with a bar and a square. So bar means average. So that's the average particle velocity. So this was just regular velocity squared. This is now saying an average of all the molecules. It's a super exciting looking law. Just wait till we use it. Very exciting. I wrote way too big. Let me finish my thoughts over here. Okay. So if the gas kinetic energy is directly related to mass, this also means that the average particle velocity is related to mass. So as long as we're at the same temperature, like I'm looking at a few samples of gases at the same temperature, the heaviest gas will move the slowest, will have the slowest average particle velocity. So you can see this in this graph. There we go. So here I am, one temperature, like 3 different gases. I have chlorine gas, nitrogen gas, and helium. Chlorine has a mass of 70.9 grams per mole. This is 28, and this is 4. And here are my speeds. Chlorine is on average going, what would you call that, 250. Nitrogen is on average going about 500, and the helium's going almost 1,000 meters per second. So the heavier the gas, the more kinetic energy it takes to get it going. So overall, it's going to move slower, which is what you already know, right? I mean, you can relate that to regular things, that heavier objects take a lot more effort to get going, and in general will never go as fast as lighter objects. Actually, I'll just call this speed. Speed. So speed of heavier objects less than speed of lighter objects. Good. How is kinetic energy related to temperature? All right, so the average kinetic energy is also proportional to temperature. through that equation that the average kinetic energy is equal to 3/2 the gas constant times temperature. Combining that equation with the one we just had that related moles and mass and average particle velocity with some math magic that I, again, would love to derive with you, but I'm assuming you just want to get to the end. All right, so combine those two equations. All right, so taking this equation and combining it with the one we had that dealt with mass, we get the u, it's now called root mean squared. It's saying that I took the square root of the average, which would be the root mean squared. That now equals square root of 3 times the gas constant times temperature, Avogadro's number, mass. But those Avogadro number times mass is the same as molar mass in kilograms per mole. So that weird, it's kind of an M-ish, a capital M that's, has like things in the bottom. Yeah.
It should be in Kelvin.
Yes. Yep, because R is in Kelvin. So yep, temperatures have to be in Kelvin. All right, so this means so velocity is directly proportional to the square root of temperature. So as temperature increases, velocity increases. Which is what we know about gases anyway, right? The hotter the gas is, the more it moves around, the less dense it gets. You get your hot air balloon to float. So how about we do one example that shows this. Oh, sorry. Snazzy graph. Look, I got nitrogen at cold, less cold, pretty hot, moving faster. Ta-da! Okay. All right. The last thing in chapter 5 is this. So let's calculate those velocities for two types of gases, both at the same temperature. Which would be faster moving? So if I'm at the same temperature, is it going to be a temperature effect or a molar mass effect? Molar mass effect. So if I tell you that oxygen has a molar mass in the weird units that we use, kilograms per mole, and argon has a molar mass of which one of those is heavier? Argon is heavier, so which would you expect to be slower? You guys are correct. Good. We'll do a little math just to show that you're right. Because the units in this problem is weird. We'll do oxygen first. All right, so those are the M's. So we plug in 3 times the gas constant times 298 Kelvin over, let's see, oxygen's molar crazy mass. So 3 times the gas constant times temperature divided by these molar masses. So So this is just oxygen. All right, moles cancel out. Kelvins cancel out. Let's see what this is numerically. Okay, let's see. 3 times 8.314 times 298 divided by 3.2, negative 2. Square root of 2.32 times 10 to the 5th joules per kilogram. It's odd looking. All right, joules per kilogram. One, if you square root of that, you'd have square root joules, square root kilograms, which is not a unit. But to the rescue, joules happens to be a kilogram meter squared per second squared. Look how handy that is. So now I have, this was joules, this is still 1 over kilograms. Now the kilograms disappear, and now I have things that were squared, and that will be just normal, which makes sense, right? Because what do we measure speed in? Meters per second, and now we're in meters per second. So let's see what that turned out to be. 481.9 meters per second. If you do the other one, which you should probably do on your own, I'll just tell you what the answer is so you can double check your math. Argon has a root mean squared speed of 431 meters per second, which is slower than oxygen, which you knew to be true anyway. But now you have numbers to back up your factual statements. Yay. All right. We have our group quiz, and when I see you next Wednesday, bring your chapter 3 notes. And we'll start talking about balancing equations and moles and all kinds of stuff like that. Maybe a little bit of naming. One, you don't need a calculator, and 2,